Welcome to Techno Sapiens.
Welcome to This Explainer. Today, we're looking up, quite literally, at a massive piece of engineering hiding right in plain sight. Have you ever been driving down the road, looked out the window at the power lines, and noticed something kind of curious? Some of the wires stretching from pole to pole are super thin, while others are these incredibly massive, thick cables. It's one of those everyday sights we completely take for granted. We've all seen them, but let's ask the obvious question here. Why the huge difference? Are the thicker power lines simply built that way so they don't snap in the wind? Or is there a deeper, much cooler mystery here involving electric current, resistance, and the sheer amount of power we're moving across our grid? Well, it turns out it's a brilliant mix of physics and engineering. Section 1. Electricity needs a path. To crack this mystery, we first need to look at the fundamental way electricity travels from point A to point B. Okay, let's think of an electrical wire exactly like a road system. Imagine a small, narrow, single-lane country road. It works perfectly fine for a handful of cars. But what happens if you try to force rush-hour highway traffic onto that tiny road all at once? Boom, total traffic jam. Electric current works the exact same way. A thin wire just has way less physical space for electric current to flow. But a thicker wire, that acts like a massive multi-lane highway, giving the electrical charge a much larger path. Because of this extra space, thicker conductors can carry far more current safely without causing an electrical traffic jam. Section 2. Dangerous heat. Now here is where that electrical traffic jam becomes our absolute biggest hurdle. Here's the deal. Every single electrical wire in existence, no matter what it's made of, fights back a little bit. That's electrical resistance. Think of resistance basically like friction. At a microscopic level, as electrons are shoved through the wire, they are constantly crashing into the metal's atoms. Just like vigorously rubbing your hands together, all those countless tiny collisions create friction, inevitably converting some of that precious electrical energy into wasted heat. It doesn't just vanish, it literally heats up the physical metal of the wire. And this heating effect isn't random at all. It follows a very specific mathematical rule. The heat generated is proportional to the current squared, multiplied by the wire's resistance. When a large current flows through a wire that has too much resistance, the amount of energy converted to heat spikes dramatically. I want you to focus on that little squared number right there, because that is the crucial point. Because the current is squared in this equation, shoving a massive amount of current through a thin wire doesn't just make it a little bit warm, it skyrockets the heat exponentially. A thin wire carrying a heavy electrical load can quickly become so dangerously hot that it could glow red, melt, or just fail entirely. So, how do engineers fight this dangerous heat buildup? They use thicker wires. By increasing the size of the wire, you give it a larger cross-sectional area. That larger area fundamentally drops the electrical resistance of the wire. And as we just saw from our equation, lower resistance directly means way less energy is wasted as heat. Problem solved. A thicker wire effectively stops the whole system from dangerously overheating when placed under a heavy load. Section 3. The high-voltage solution for transmitting more power. But hang on a second. As power demands grow from a small neighborhood to a sprawling, massive city, the power demand goes through the roof. Logically, if current keeps increasing, wouldn't we eventually need impossibly massive wires, like stringing up solid copper cables the size of tree trunks? That would be incredibly heavy and, frankly, ridiculous. Instead, engineers use another elegant little formula to get around this. Electrical power equals voltage multiplied by current. Power is the total package of energy we need to deliver, but because it's a multiplication of those two different factors, engineers get a choice in how they deliver it.
Here's how that trade-off plays out. If you try to transmit huge amounts of power using low voltage, you are forced to use incredibly high current. And as we know, high current means severe heat loss and impossibly thick wires. But by drastically cranking up the voltage, engineers can transmit that exact same total amount of power with a fraction of the current. Less current equals significantly less heating loss. This is exactly why long-distance transmission lines use extremely high voltages. It completely bypasses the severe heat problem.
Section 4. Massive conductors in engineering the grid. Let's see how this all builds into the physical reality of the heavy-duty lines we see strung across those huge metal towers. If you ever got up close to those large transmission conductors high in the air, you'd see they aren't just giant, solid tubes of metal. They are highly complex, carefully engineered cables made from multiple individual strands twisted together. This multi-stranded design is absolutely vital. Yes, it provides excellent electrical conductivity to keep that resistance low, but it also gives crucial mechanical strength and flexibility. These things have to stretch massive distances between towers and survive intense wind, freezing rain, and searing heat, all while safely moving huge amounts of current.
Actually, sometimes when you look up at a massive transmission tower, you aren't even seeing one single thick wire per connection point. You're seeing a group of multiple thick conductors separated by little metal spacers. We call this a bundled conductor. Engineers group them together to act as a single electrical phase. This brilliant setup improves the overall electrical performance of the transmission line, letting them handle crazy high power levels safely and efficiently. Every single detail is perfectly calculated.
So, next time you are out on a drive and you catch yourself staring at those massive transmission lines cutting across the sky, remember, their size is absolutely not random. From the thinnest local lines to the thickest bundled conductors, what you're looking at is a masterclass in fighting electrical resistance. It's a system perfectly designed to balance voltage and current, conquer the dangerous problem of heat, and keep our modern world completely powered up. It really makes you wonder, doesn't it? What other huge engineering secrets are hiding right in plain sight, just waiting for us to look up?